Hello, my name is Andrew, and this is my presentation for the Constant Velocity Lab for Physics 2211. For this lab, I pushed a ping pong ball and observed it rolling across my desk at constant velocity. The system is a ping pong ball, and the surroundings are the desk, my hand, and the air. The purpose of this lab is to show the concept of constant velocity and how no force acts on the ball when it travels at constant velocity. It also shows how using a tracker is more accurate at determining the velocity of the ball than using a formula that assumes no friction or air resistance. The lab also makes use of a computational model in Python for tracking the position of the ball by using the average velocity in order to put the ball's position on a graph. Newton's first and second laws are important in this lab. Newton's first law states that an object will remain in constant velocity or rest unless acted on by an external force. This lab explains why, once I push the ball, it remains in constant velocity due to the lack of external forces acting on it. Newton's second law states that force is equal to mass times acceleration. This shows how net force of the ping pong ball is 0 newtons, because the acceleration is 0. The acceleration is 0 because the ping pong ball is moving at a constant velocity and without a change in direction. This video shows the tracker tracking the ping pong ball as it moves across my desk. The ball moves right along the pink x-axis, and the red dots track its position as time passes. These data points give the data necessary to make a position versus time graph. The blue line labeled 1.06 meters is the scale that the tracker uses to determine the distance that the ball travels. 1.06 meters is the length of my desk. The tracker data shows the position time graph becomes less steep, which means that the ball slows down as time passes. I'll explain why this is later. The y-axis is irrelevant to the data because the ping pong ball is only moving on the x-axis. The data used for the Python computational model includes the displacement of the ball, or the desk length, which is 1.06 meters. The time elapsed is 4.93 seconds. The average velocity is displacement over change in time, which is 0.215 meters per second. It should be noted that the video was shot in slow motion, which is why that number is so low. I used 1 as the mass, since the mass didn't affect the calculations later on, since the net force is 0. I set the ball velocity equal to the average velocity of 0.215 and kept the initial position of 0, 0, 0. I made the net force the 0 vector, since the net force is 0. I used the modified version of the velocity update formula by substituting acceleration for force over mass, since again the net force is 0. I used the standard position update formula for the ball position. The predicted position time graph is a straight line because I predicted that the ball moved at constant velocity. The observed graph becomes less steep due to air resistance and friction, which slow down the ball. Using manual tracking may have produced some differences also because the tracker doesn't perfectly track every point like a computational model does. If I flip the axes, the ball would have had the same speed, except instead of the position becoming more positive, it would have become more negative, and the graph would have sloped downwards. How many pushes and pulls act on the ball? It's difficult to determine how many forces are acting on the ball so that it has a 0 net force. But we know that the actual net force isn't 0 due to friction and air resistance acting upon it. There are some sources of error in the lab, such as not including air resistance and friction in the computational model, and plotting too few points of data on the tracker. More of these points would have given a more accurate position time graph of the ball. Thank you for listening to my presentation.